In this video, we're going to look at how to use partial fractions to evaluate integrals of rational functions whose denominators contain quadratic factors. Specifically, we're going to be looking at rational functions where the denominator contains an irreducible factor of the form x squared plus bx plus c. Notice that if the quadratic factor is not irreducible, we should factor it completely into two linears and then follow the process for partial fractions with linear factors. So if our denominator has such a factor, then our partial fraction decomposition is going to contain an expression of the form ax plus b over our quadratic, x squared plus bx plus c. And here a and b are constants. And so notice here that our numerator is going to be a linear function, as opposed to when we have linear factors and the numerators are just constants. We need to have a full linear factor here in order to have the correct partial fraction decomposition. Although in this video we're concerned primarily with single irreducible quadratic factors, if we had a repeated irreducible quadratic factor, we would handle it in an analogous fashion as how we handled repeated linear factors in our denominator. In this example, we'd like to evaluate the integral of 2x squared minus x plus 4 all over x cubed plus 4x dx. Since our numerator has a smaller degree than our denominator, we can proceed with using partial fractions. The first step is to factor our denominator completely, and here our first step would be to factor out a common factor of x, and the resulting remaining factor would be x squared plus 4. And this is a sum of two squares. We have x squared plus 2 squared. And as you hopefully recall from algebra, when we have a sum of two squares, these expressions will never factor. A difference of two squares will indeed factor, but a sum of squares never factors. And so here is an example of an irreducible quadratic in our denominator. So we need to use the partial fraction decomposition with a linear and a quadratic factor. So here we have x times x squared plus 4. So we look at each of these two terms separately. We have a linear factor of x, so that would be a over x, simple term there. And for our quadratic factor, we have x squared plus 4, which will be our denominator here. And in our numerator, we need a linear factor, not just a constant. So maybe bx plus c, where b and c are some constants. So here we have our linear term over our irreducible quadratic. And this will be our partial fraction decomposition. We can then multiply by our denominator on the left-hand side to get rid of all of those denominators. And so we're left with 2x squared minus x plus 4 equaling a times x squared plus 4 plus bx plus c all times x. Now we need to find the values of a, b, and c in this expression. We can find the value of a pretty easily by letting x equal to 0. On the left-hand side, when we let x equal to 0, the first two terms will vanish and we're just left with 4. And on the right-hand side, we notice that the whole bx plus c term is being multiplied by 0 here. And so we're just simply left with a times 0 squared plus 4, which is 4. And so we get that a is going to equal 1. And so this is the easy coefficient to find. Now, we might try to substitute other values of x into the equation to solve for b and c, but what we're going to find is that other than when x is 0, we're not able to eliminate b or c from our equation. And so regardless of what other value of x you pick, you're going to have two unknowns in your equation, and that's just a situation that cannot be solved. And so we need to do something else here in order to find the values of b and c. There are a couple different approaches that we can use here. The one we're going to follow in this video is to first substitute the value of a in for the coefficient of a in our equation. So here we're going to replace the a with 1. And then we're going to expand out this entire equation and compare both sides. So when we replace a with 1, we get the equation 2x squared minus x plus 4 equals x squared plus 4 plus bx plus c times x. We can distribute the x in that last term on the right side to get x squared plus 4 plus bx squared plus cx. We now want to group like terms. And so we see we have an x squared plus bx squared here. And so we can rewrite that as 1 plus b times x squared. Just like if we had 2x squared and 3x squared, we could add them together to get 5x squared. Here we have 1x squared plus bx squared, which gives us 1 plus b times x squared. We also have the term cx and the constant value of 4. And now we can look at the left-hand side and the right-hand side of this simplified equation and compare like coefficients. For example, we might look at the coefficient of x squared in each side. On the left side, that would be equal to 2, and on the right side, that's going to equal 1 plus b. And in order for these two sides to be equal, all of the coefficients of the corresponding powers of x need to be equal. And so from observing the x squared coefficients, we see that 2 has to equal 1 plus b, and therefore b must equal 1. We can do the same thing with any other term, so we can compare, for example, the coefficients of x. In the left-hand side, that would be a negative 1. There's an implicit 1 there in front of the x. And on the other side, it is a c. And so from that, we see that we must have c equal negative 1. There's nothing even to solve for there. We get that straight away. And so this gives us our values of b and c, which combined with the value of a that we previously found to be 1, gives us all of our values for our partial fraction decomposition. So as you'll recall, we had a partial fraction decomposition of a over x plus bx plus c over x squared plus 4. And substituting our values in, we have the partial fraction decomposition 1 over x plus x minus 1 over x squared plus 4. And for purposes of evaluation for our integral in the next step, we're going to rewrite the x minus 1 over x squared plus 4 as x over x squared plus 4 minus 1 over x squared plus 4. And this will allow us to evaluate the integral of 3 different terms using 3 different techniques. This means that our original integral of 2x squared minus x plus 4 over x cubed plus 4x dx can be written as the integral of 1 over x plus x over x squared plus 4 minus 1 over x squared plus 4 dx. We know the first of these expressions can be anti-differentiated to give the natural log of absolute value of x. However, the other two both require a little bit of work to find the antiderivative. For the second term, the integral of x over x squared plus 4, we need to do a quick substitution. We can let u be the denominator, x squared plus 4, which means that du will be 2x dx. And since we only have x dx, we need to divide by 2 to get du over 2 to equal x dx. We can substitute all of this into our integral, and we end up with the integral of 1/2 times the integral of 1 over u du, which will be 1/2 natural log absolute value of u. And we can substitute in x squared plus 4 for u. And to get 1/2 natural log of the absolute value of x squared plus 4. So this will be the value of our second integral. And if you would like, notice that you could leave off the absolute value bars in this particular case, since x squared plus 4 will always be positive. But we'll leave it here just to be absolutely complete. But they can be omitted from the second term. Now we move on to our third term here, and we want to compute the integral of 1 over x squared plus 4. In order to compute this integral, what we can do is factor out a 4 from the denominator of this expression, and so that'll give us a 1/4 constant outside of the integral. And in the denominator, we'll have x squared over 4 plus 1. We can rewrite the x squared plus 4 in a convenient way. We can think of that as x over 2 quantity squared. All plus 1 in that denominator, all under 1 dx. And now this integral looks a lot like the integral for the arctangent function, except we have an x over 2 instead of just an x that's being squared. And so we can fix that with a simple substitution. We can let u be x over 2. Du would then be 1/2 dx. And since we only have dx in our expression, we can multiply both sides by 2 to get 2 du equals dx. And now we can make this substitution. We have 1/4 of the integral of 2 du, so we can multiply by 2 out front, of u squared plus 1 du. 1/4 times 2, of course, is just 1/2. And our integral here, integral of 1 over u squared plus 1, is just the arctangent function of u. And we can go back to x, and we get 1/2 arctangent of x over 2. And that is the value of our third function in our antiderivative. So we have plus 1/2 arctangent of x over 2. And all of that plus c. And so this will be the final antiderivative, or the final value for our integral, of 2x squared minus x plus 4 over x cubed plus 4x. If you'd like to try a similar example, pause the video and evaluate the integral of 2x minus 3 over x cubed plus x dx. Resume the video, and the full solution will appear in a few seconds. The denominator factors as x times the irreducible quadratic x squared plus 1, and so our partial fraction decomposition will have the form a over x plus bx plus c over x squared plus 1. We clear the denominators to get 2x minus 3 equals a times the quantity x squared plus 1 plus bx plus c all times x. We can let x equal to 0, and once we do that, we get exactly negative 3 equals a, and therefore a will be negative 3. We can substitute negative 3 in for a and distribute there to get that 2x minus 3 equals negative 3x squared minus 3 plus bx squared plus cx, which we can rearrange and combine like terms to get negative 3 plus bx squared plus cx minus 3. We can then compare like coefficients to find the values of b and c. To find b, we look at the coefficient of x squared on each side. On the left-hand side, notice that there is no x squared term, which means our coefficient is 0. And so we know that 0 is going to equal negative 3 plus b, or b is going to equal 3. We can also compare the coefficients of x, which are 2 and c respectively, and so we know that c is equal to 2. And here we have all three of our values for a, b, and c. Substituting these values into our partial fraction decomposition gives us that our integral is equal to the integral of negative 3 over x plus 3x over x squared plus 1 plus 2 over x squared plus 1 dx. The first and third term have elementary antiderivatives. We have negative 3 natural log of absolute value of x for our first term, and in our third term we get simply 2 times the arctangent of x. The middle term has an antiderivative of 3/2 the natural log of the absolute value of x squared plus 1, where again the absolute values can be omitted there since x squared plus 1 is always positive. In order to see where that antiderivative comes from, we can make a standard u substitution of x squared plus 1 so that du over 2 is equal to x dx. When we substitute that in and arrange for the constants to be pulled out front, we get 3/2 integrals of 1 over u du, which is 3/2 natural log of absolute value of u, or 3/2 natural log of the absolute value of x squared plus 1. We can substitute that in for our middle term, and we get an antiderivative here of -3 natural log of absolute value of x, plus 3/2 natural log of the absolute value of x squared plus 1, plus 2 times the arctangent of x, plus c.